probably heard of Sir Isaac Newton. He's a very famous British scientist who revolutionized so many different fields. For example, he developed the modern telescope, he developed calculus, he developed the law of universal gravitation, and in 1687, he published this work. This work, which is titled in Latin but translates to The Mathematical Principles of Natural Philosophies, in this work, Newton laid out his 3 laws of motion. And these were really revolutionary because they looked at our macroscopic world around us and described objects' motion based upon force and interactions. And this was really important because it was a new step, a new direction from what previous philosophers had said. Before we had Newton, we had famous philosophers like Aristotle, and we also had Galileo. So when Newton came along and came up with these laws of motion, they were a lot more modern than what previous philosophers had hypothesized. First law of motion. You all are intuitively aware of what this law actually says. So let's go through an example to kind of get your brain primed. Let's consider an example of a skateboard and a skateboarder. So pretend this is you skateboarding, okay? We know that the skateboard isn't just going to miraculously move on its own, right? You have to supply a force to get this skateboard moving. And conversely, we know that either the friction of the road or an obstacle has to happen, an external force has to happen to slow you down. Think about if you're skateboarding and you come across a curb, right? And you hit that curb. I want you to think about what happens to the skateboard versus what happens to you. So you're skateboarding and you hit a curb, what happens? To answer this question in terms of physics, we're going to turn to Newton's first law of motion. In Newton's first law, it states that an object at rest stays at rest. So I have books behind me in my bookshelf, right? Those books aren't just going to miraculously appear in my hand, right? I had to apply a force, pick it up, and place it in my hand. Conversely, the first law also states an object in motion stays in motion without external forces. So again, think of our skateboard. It stays at rest unless we apply an external force to get it moving. And imagine you are skateboarding on a frictionless surface. Once you start going, you're going to keep going, right? Unless something slows you down. Now that we have defined what Newton's first law states in terms of physics, let's revisit the skateboard problem. So again, you have to apply a force to get the skateboard to keep moving. The skateboard then hits a curb, so it comes upon an external force that wants to stop it. But I asked you, what happens to you? Remember Newton's first law, an object in motion wants to stay in motion. So hopefully you're wearing a helmet to reduce any injuries, but if that skateboard hits a curb, you're probably gonna keep going, right? You are already familiar with how Newton's first law works in your day-to-day life. Think about if you're in a car, if the car starts or stops. You can think of yourself as an object in motion or at rest, right? So next up, I want to show you a pretty cool demo, and then we're going to jump into some practice problems. Okay, before we get into problem solving, I want to give you a pretty cool demo. Here are our materials. We have a cardboard tube, we have eggs, we have a piece of cardboard, and we have a beaker full of water with food coloring in it. What we're going to do is, again, show Newton's first law. Here's the setup. We have our cardboard on top of our beaker. We have our cardboard tube on top to hold our egg. Now what we're going to do is supply a quick external force to the flat piece of cardboard. Now before we actually do this, I want you to think about what will happen to the egg. Do you think it's going to go flying with the cardboard? Do you think it's going to drop into the beaker? Take a quick second and think about it. Is that what you thought would happen to the egg? Think about it. Why or why not? And in the context of Newton's first law of motion. Come on, let's do some problem solving. So far, we have looked at Newton's first law more qualitatively. So let's take a quantitative approach instead. We have said that Newton's first law can be described as an object in motion stays in motion, or an object at rest stays at rest. And in all of the examples we have looked at so far, we have seen how forces affect the motion of an object. And we know that a force acts upon the object, and that we can describe the force as a push or a pull. However, in the case of an object's macroscopic motion, so again, the things you see in everyday life, a car driving down the road, or you walking down the sidewalk, we are looking at the net force acting on an object. And what do I mean by that? Well, in most scenarios, we have more than one force acting on the object at a time. Let's take, for example, let's say you are sitting at your desk. So we have a chair, that's a chair, and we have you sitting there, and then we have a desk, what forces are acting on you sitting in that chair? We know that we have the normal force of the chair acting on you. We also have the force of gravity. Maybe your feet are touching the floor, so then we also have the interaction between the normal force of the floor and your feet. Let's say your hands are touching your desk. You also have forces in action there. But what is my net force in this case? Does everything balance out? Does it not balance out? And how does that affect the motion of an object? Let's consider a free body diagram of a person just standing on a floor. They're not moving, they're just standing there. I know that I have the normal force of the floor pushing back up on this person, and I also have the force of gravity. this person is static, they're just standing there, we know that these forces are balanced. Again, an object at rest stays at rest unless we have an external unbalanced force. I added the unbalanced there, we'll get to that, to cause motion. Let's say we have your physics textbook on a table. Again, we know that we have the normal force, we know we have the force of gravity, and right now, at this moment, that textbook is not moving, we have balanced forces. But let's consider if an unbalanced force acts upon this textbook. So the forces are balanced in this direction, but what if we give the textbook a push? We have a F push here. In this case, our forces are unbalanced, so unbalanced, and because they are unbalanced, they cause motion. Again, back to Newton's first law. It stays at rest, or it stays in motion, unless an unbalanced external force acts upon the object. Next, I want you to pause this video, and I want you to work on numbers 1 and 2 by yourself. Then we will regroup and go over the answers. Okay, let's go over numbers 1 and 2 on the practice worksheet. For number 1, the answer is that the car is slowing down. It was initially moving leftward, but due to the 8,000 Newton force acting in the opposite direction from the direction of its motion, it is now slowing down. So let's break this apart to really think about what's going on in this scenario. To answer these problems, first you have to remember that force is a vector. So we've gone over vectors and scalars before, but let's do a little refresher. What two components does a vector have? It has magnitude, and it also has direction. So not only does the numerical value matter, the magnitude, but it also matters in what direction the force is pushing or pulling. And just for a little review, what does a scalar have? A scalar, if you remember, only has magnitude. It doesn't matter about the scalar's direction. So, what is an example of a scalar then? Think of something like mass, or we'll get to this later on, but energy or volume. We don't think about an object's mass sitting in a northbound direction. No, we just care about the actual magnitude of the value. But for force, the actual direction that the force is occurring does in fact matter, and that is at the heart of this problem in number 1. Let's dissect the different forces that are occurring on this car, on this vehicle, and let's think about if the forces are balanced or unbalanced. Let's first look at the y direction of the car, the forces occurring in the y direction. So I'm going to draw my car as a free body diagram, so a force diagram. So I have my car, and looking at the forces in the y direction, so just in that vertical component, right? So we know that we have 2,000 newtons of force pointing downward, and we know what this force corresponds to, right? The car is on the earth, this corresponds to the force of gravity. And I'm going to assume that this car is actually on the road, on a flat surface. So we know that if the car has 2,000 newtons of force pointing downward from gravity, the road is exerting an equal and opposite force, 2,000 newtons, from the normal force. And I know that these forces are in fact balanced because the car is not breaking through the surface of the earth, hurtling towards the center of the earth, so it's just exerting its force of gravity. And we know that the earth is not, hitting the car upward into the air. These forces are balanced. The car is just traveling along the actual flat ground. The forces in the y direction are, in fact, balanced. Now let's look at the forces on this car in the horizontal direction, right? So we have our car, and we have 6,000 newtons of force going forward, and we have 8,000 newtons of force pulling the car backwards. So just thinking about how a car works. So the car is on the ground, right? This means that the car has been traveling forward at 6,000 newtons, so it's been traveling, right? It's moving forward, and we are told in the start of the problem that it is in fact moving forward. What does this 8,000 newtons correspond to then? Well, it would have to correspond to a braking force. So you're in the car traveling forward 6,000 newtons, and then you hit the brakes and you apply 8,000 newtons of force. Based upon the fact that these magnitudes are not the same, we know that these forces are unbalanced, right? So bringing this back to Newton's first law, an object in motion will remain in motion unless an external unbalanced force acts upon it, right? So this car, if we ignore friction, we just continue along unless we brake and we apply enough braking force to overpower that forward motion. So these forces are in fact unbalanced. Additionally, I want you to think about how forces, again, are vectors. So they have direction and magnitude. We can consider, this is our car, we can consider this direction, the plus x direction, and the opposite direction as the negative x direction. Again, this is just signs. You could flip the signs, that's totally fine. They will mean the same thing, that the car is braking. I've just assigned a certain positive or negative to indicate that, right? So if this is plus 6,000 newtons and this is minus 8,000 newtons, that means collectively the net force acting on the car is minus 2,000 newtons, and this corresponds to the braking force. So you can see that we're taking an example of a car, traveling along and then braking, and we're applying a physics lens to it. We are analyzing it through net forces and unbalanced forces. Okay, let's move on to number 2. So the answers are, for A, our net force is 40 newtons in the leftward direction. And for B, we have 25 newtons in the upwards direction. Okay, let's break this down using our sign conventions for the directionality of forces to make this a little bit more concrete. So in A, we have a box, and it is experiencing 20 newtons of force in the rightward direction and 60 newtons of force in the leftward direction. What I can say my sign convention is that in this direction it's negative x, and this direction it's positive x. You could also flip-flop these around as long as you are consistent. If you're consistent, it physically means the same exact thing. Okay, so if we have plus 60 newtons and minus 20 newtons, well, cumulatively, that means we have positive 40 newtons. So 40 newtons, again, in that leftward direction. Let's apply the same thought process to B. So we have a box, and we have 50 newtons of force in the upward direction and 25 newtons of force in the downward direction. I can make my sign convention such that the plus y, remember we're in the y-axis now, plus y is up, negative y is down. So again, we have plus 50 newtons and we have minus 25 newtons. And when you think about those collectively, that means we have plus 25 newtons, so that's the upward direction. Again, you have to make sure you're thinking of the forces in terms of directionality, because those are important. You know, if you push a box 50 newtons to the left, that's physically different than pushing it 50 newtons to the right. So make sure you're just being consistent with your directionalities for your forces. So why is this net force, why is thinking about this net force important for understanding Newton's first law? Well, again, we've said that an object in motion stays in motion or stays at rest if it was at rest in the absence of an unbalanced force. So, by understanding how the forces collectively affect an object is important in understanding the object's momentum. So understanding collectively how the forces on an object are affecting the motion of that object is important. That helps define how the object is or isn't moving. I want you to work on the rest of the worksheet by yourselves. So you have numbers 3 through 6, in which we revisit the egg drop and describe it with force body diagrams. And in the next Zoom class, we will go over these problems and